Okay, so this is so at Shmoocon. Okay, I guess I'll introduce myself. So my name's Sharad. I'm the current reversing IPG lead here. And today I'm going to go over the Shmoocon Ret2 challenge. So if you went to Shmoocon, which I actually didn't, this is the Ret2, which is Ret2 Systems, which is a company. They had this challenge. They do a yearly challenge. Last year was Pwn. This year was reversing. So this is actually pretty interesting. The challenge is based on a game called Mastermind. And in the game Mastermind, the way it works is that you're given a code and you have to progressively guess that code. So I guess I can run this and kind of show you how that entire thing works. How do I get the debugger? Debugger broken? What? Okay. There we go. We can run it here. So we have a code and we have to guess the colors. The possible colors, there's a bunch of colors that are possible. But so for example, you could guess red, red, blue, blue. And then it'll tell you red, red, blue, blue. And this right here, this is going to be your code. And if your code is correct, so if the color is in the right place, I think it's going to be black. Yeah. If the color is in the code, but it's not in the right place, then it's going to be white, which it is in this case. So that means in this specific case, the red is in the code, but it's not in the correct position. So you have to play this game 9 times. You have to play it once on easy, 3 times on hard, and 3 times on medium, and 5 times on hard. And in easy, you get 7 guesses. In medium, you get 5 guesses, and in hard, you get 3 guesses. So basically, you're not solving this manually. You have to reverse it. So I guess we can just get into the reversing. So just like regular war games, you get a little bit of C source code to start off with. So let's just go through that. We started with main. You have init war game. This does some war game specific stuff. It's pretty much irrelevant. You can pretty much ignore it. And then we get the create new game. This creates a game state structure, which is up here. It's a malloc structure. And we set difficulty to 1, so we start out at easy. We require 1 win, just like because easy we require 1 win to continue to the next difficulty. We have guesses allowed, so we have 7 guesses. The macro guesses allowed is up here, 7 guesses. And then we seed it with the time. This is important right here, this line right here, because specifically in medium and hard, the code is generated based on a seed. And because it's time seeded, we can essentially use the current time, to get the right seed and to regenerate all the random numbers. So that's how we go about doing that. Once we generate the game, we start out the game. So this, while difficulty is less than 4, so while we are essentially 1, 2, so the 3 difficulties are 1, 2, 3, so easy, medium, hard. So while the game is continuing, play the game, wins required number of times. So wins required increases by 2 every game. So play the game once on easy, 3 times on hard, 3 times on medium, 5 times on hard. Then play a round. If we don't win the round, which is the case where I think play round returns 0, then end the game. Otherwise, go to the next difficulty. Pretty simple. So let's go into play round, because that's kind of all the important stuff. So we take in a game state, and then we set all our guesses to 0. That's cool, I guess. We generate the code. This is what we need to be reversing right here. And this, we don't have the source code to, obviously, because we're reversing it. So we generate the code, and then that sets this in here, the code. We're going to figure out exactly what that's doing. And then we go through, and then we allow the player to guesses allowed number of times. If the code is the same, return 1. Result is 1, and then return 1. So that's that. So now we move on to the assembly. So we go to, where do we go? We go to generate code. Let me try to move this here. Yeah. Generate. That's not what I'm looking for. Generate code. There we go. So generate code's pretty simple. So generate code takes in one argument, which is going to be the game state. So game state right now at the top, let me write that down actually. So game state is in RDI, because RDI is the first argument in x64. So now we continue, go here, we save the game state into RBP -8, that's important, and then we move it into RAX. And then we get RAX plus aux24. Actually, I'm actually going to go here, because I did write this down. So a lot of discussion for this was actually done in a thread on Discord, so if you want to look at that, if you're interested in that, that's also good to look at. Where is the config section? Oh yeah, I'm actually in it. So this is the game state structure right here, and these are all the offsets for the structure. So at an offset of aux24, which is, I believe, what's that going to be in hex? I mean in decimal. Aux24 in decimal. Is it 24? What?
Quick math.
Quick math, indeed.
Yeah.
That's 36. Yeah, because 16 times 2 plus 4. So at an offset of 36, you have the difficulty. So right now, what we're getting is EAX contains the difficulty. So we compare the difficulty to 1, so that's easy. So if the difficulty is 1, then we go here. Wait, no. If the difficulty is 1, we go to easy. And then if the difficulty is 2, then we go to medium. If the difficulty is 3, then we go to hard. Pretty simple. Yeah. So let's start with easy. Because easy, we pass in, so generate code easy once again takes in the game state, because we take in RBP, we move RBP -8 into RAX. RBP -8 contains the game state because it was stored up here, this line specifically. So we've taken the game state and then we move that into generate code, then we move into generate code easy. Okay, so this is where the hell begins. So yeah, RBP, so we move RDI into RBP -18. That is our game state once again. So our game state is in RBP -aux18. Move that into RAX. And then we get RAX plus aux30. So RAX plus aux30 will be the offset into the game state. So if we go back to our offsets here, aux30 is 48. So right now we're getting the seed. So the important thing to remember is the seed right now is the time that we set in the source code up here. So that we set that in create new game. GS seed is equal to time. So right now, where EAX contains the time. We AND EAX with aux1F. So I kind of explained why we AND it, and that gets the lower 5 bits of the time. So because we get the lower 5 bits of the time, there's only 31 possible times that are real. So we get this as a result of this AND. EAX can only be between 0 and 31, is what I'm trying to say. Yeah, we move that into RBP -8, and we move 0 into RBP -4. RBP -4 in this case is going to be our counter, because there's a for loop actually here. We compare the counter to, now we, I guess, start our for loop at this point. We compare the counter, which is RBP -4 to 3. If it's less than or equal to, then we go into our for loop. If it's not, then we leave. So now the real shit kind of happens. Time in EAX. So we get this secret pad. We move into RCX. We move down to EAX. Yeah. What else is going on here? We increase the time. Time now in EAX. We increase the time. Then we commit time plus 1 to memory. So yeah, we increment the time every loop, and then we add time plus secret pad. So I guess what's going on here is that we get this number from secret pad, and this secret pad is something actually in data, so we can look at that right here. If you scroll down far enough, it's going to be this number, the 0823040 number right here. We move that into RCX, and then we move the time into EAX, and then we add 1 to that time. And then what else do we do? We do time plus secret pad right here. That's the important thing. And then we get color from the color list. Oh, that's actually, oh, I remember. Okay, I remember what's going on here. Secret pad's actually an address. Secret pad's an address. So so this is actually a little endian address. So if you write that out in little endian, that's actually going to be, what's that going to be? It's going to be box 40, 2308. That's going to be that. And then if we go to that address in the data section, we'll actually find that it's actually pointing. Hey, fuck. Oh, shit. Oh my god, I'm getting tilted. 23, where is this address? I missed it by a mile. It's actually gonna be right here. It's gonna be the string. So what we do, so what essentially is going on here is that we go back to the disassembly. We add time and 31. Wait, what? Time and 31 plus that secret pad address. That's what we're doing here. And then what we do with that is that that's a new address. That's an offset into the string. And then we do this move right here. So now we get the color from this color list. And then we move that into gscode.counter. Yeah. And if we go to the Python, that's kind of what I do here. That's kind of what happens here, is we start getting the time. We get this, I copy this color string into that easy color string. I mod it by 32, or I guess you could actually just and it by 31. That would be the same thing as modding it by 32. I'll replace that with mod 32. And then I just send the 4 colors between there. Yeah, that's easy. Easy is kind of a pain in the ass. I kind of hate this. Yeah. Do you have any questions about easy? I don't know, that was a lot. Before I move into medium. There's a lot here. There's a lot here. I don't even know. Those are my notes. So the reason why in the Python, I guess I do ind easy to ind easy plus 4 in color string is because time is incremented by 1 every single time. So we essentially get a substring. We essentially get a substring of this string right here. We get a substring of size 4, and that's going to be our code. So if we actually run the Python here, we'll actually see that it doesn't fail. It did fail. God damn it. That happens sometimes. There we go. If we actually see it, we'll actually see that we actually did get it correct. So we actually got it all correct. So that's how you do easy. Now everything just gets way harder from here, unfortunately. So now we go to medium. As you can see, this is absolute fucking hell. I don't know who decided this would be a good idea, but they thought it would be a good idea. So you get all these notes. So now we go to medium. So we get the game state. The game state's once again an RDI. We move down to RBP minus 18. We get the time again, which is at an offset of 48. We move the time into RBP minus C. We move a temp calculation variable is actually an RBP minus 4. And we put our counter, our for loop counter, into RBP minus 8. We once again do a for loop of size 4. So we do the loop 4 times. So this is where things get kind of stupid. We get the time. We do the time XOR with this number. That's going to be with that number. We store that number into RBP minus 4. And we move our counter into EAX. And then we add this value right here, plus our I value, which is our counter. Then we move that value into ECX. we move a new value, this AAB value, into EDX. We move that. What do we do? What's even going on here anymore? ECX, we move that to EAX. We multiply. Oh, this is where shit gets kind of fun, because we multiply EDX. We run this instruction right here. What that does is it multiplies EDX with the value in EAX, but it puts the lower 32 bits of that multiplication value into EAX, and it puts the higher 32 bits into EDX. So what is actually going on here is that we have to get the, so in the next instruction, we actually work with EDX. So what we have to do is we have to get the higher 32 bits of that multiplication value, which is why in this thing right here, I had this right shift 32. So we shift right EDX 2 again. I do make a mental note here. Remember that EDX contains the higher 32 bits of the multiplication. So now we have that. We move that new value into EAX. We multiply EAX by 2. Then we add EDX, which contains that same value. So that's 3 times that value. And then we add them together again, creating 6 times this value right here. And then we subtract from this. So ECX actually contains this value up here. So we do this value, ECX, minus 6 times whatever the hell this is. Yeah. Move that value into RBP minus 4. And at this point, now we can actually get the color. Now our calculation is actually complete. So now we do RAX times 8 plus this value right here. This is actually a value in the data section. This aux603120 value. It's in the data section. So you go to the data, and then we can kind of look for that value. I think that value is right here. This G colors right here. So aux603120, that's the G colors value. We multiply that value times 8 to get a pointer. When this G colors thing is actually just an array of pointers. And it's actually a bunch of references to all of these right here. This green, yellow, blue, magenta, cyan, white. So we start out with this. This is going to be, I think this is actually going to be, I'm not sure actually, 401BED. That's actually going to be somewhere up here. What was it? 401BED. One B ED is actually going to be right here, so it's going to be red. The next one is blue, green, yellow, orange, purple, and if you go down to that G colors value, you can actually see that those pointers actually line up quite well. So we get the pointer from that. We get the pointer from that. We get the correct pointer from the G colors. We move the pointer into ECX. Actually, no, we don't. We move from that color string into ECX, and then we move our game state into RDX. We move I into EAX. And then this is where we actually set the code right here. This is actually where we do GS code is equal to our new color. And keep in mind at this point, CL is actually going to contain the actual colored letter. And then what do we do here? We move the time into that, and then we square time, which is weird. Then we do time EAX. So we get the lower 32 bits of EAX, I think here. And then we add 1 to the counter again. So in Python, what does that look like? That was a lot. In Python, it looks like this. What the hell is this? I don't know whose idea this was, but looks like that. So our medium color string is that. So that's actually the G colors. It's actually really tiny. Yeah. So our G colors string is actually going to be that. Those are going to be the letters that it's going to get. And this is where this is the calculation of the actual index into the string. And once we get that color, we add the string to our answer, and then we do this, we change the time again, which is what we do down here, is we change that time right here. And then we send our answer. So we have to do this 3 times because we do easy once, medium 3 times, and hard 5 times. Yeah. So that's what happens here. And if we look at this again, we'll actually see that this code does work. So we get medium once, medium twice, and we get hard. So we make it to hard. So what's going on in hard? Hard is somehow actually a little easier than medium. Medium's kind of hell. I don't know why, but they made it like that. Yeah. So now we go to hard. Hard we move, actually hard is a little interesting. We actually can't do hard first. You actually have to go back to this right here. This is actually where, so right now we've been using GS seed. We have not used GS RNG state yet. So we actually, what is GS RNG state? GS RNG state is actually generated by this thing called create new RNG, which is interesting. That code is a little weird. So create new RNG takes in a seed, and that seed is right now in EDI. So we push RBP, we do our function prologue, we move EDI into this RBP minus 14. And then we malloc a buffer of size aux18. And size 18. Should probably change that. That's in decimal, that's 24. So we malloc a buffer of that size. We store that into RBP minus 8. And then we move our time, which we stored up here, into EAX. And then this is where shit gets kind of interesting. We create this new structure, and I guess this kind of explains what's going on here. We have a structure of size aux18. So RNG A, which is the first part, is at an offset of 0, is time XOR aux dead beef. RNG B, which is an offset of 4, is the time XOR that. Then RNG C is the time XOR dead code. RNG D is the time XOR whatever this is. The time, and RNG E is that, and RNG F is the actual time. So I actually put this in the Discord as well in this discussion. I created a menu. This is what this looks like. This is our RNG structure. Yeah, it's gonna look like that. So time XOR that. Yeah, that's what the values of the actual structure are going to be. So keep this in mind. This is going to be used a lot in RNG and create and generate code hard. So in generate code hard, what happens? We once again put our game state into RBP minus 18. We do that, and at this point we actually get RNG state into RAX. We move RAX into RDI. So RDI right now is going to be our first parameter for XOR WOW. So we go into XOR WOW, and this is kind of stupid as well. I don't know exactly what happens here. Actually, I do know what happens here. It's just a lot of XORs. Yeah, so we store RNG. RDI contains RNG right now. We put that into RBP minus 18. And then we kind of just perform this big-ass calculation that I don't really want to explain at this point. Yeah, so we perform that calculation. I guess I can explain it, why not? So right now we start out by moving RBP minus 18 into RAX. So right now RAX contains our RNG. So that buffer that we malloced where do we malloc it? In create new RNG. Yeah. So we move RX plus aux10, which is RNG.E. So RNG.E right now is time XOR this value right here. We move that into RBP minus 8. We move that into, so we move that into RBP minus 8. So RBP minus 8 and RBP minus 4 are 2 temp variables that we work with a lot in this function. I called them X and Y. RBP minus 4 is X, and RBP minus 8 is Y. We move that into, we move the RNG.E into RBP minus 8. We move RNG.A into RB into X. We move RNG.D into EDX. And then we kind of just, essentially what happens here actually is that the values are shuffled around, and then there's some changes to certain values here. Yeah, so at the end of this, you get like almost like a rotation of the RNG state thing that was generated in create new RNG. So you get a rotation of that, and that's used in generate code hard. So generate code hard, it's actually surprisingly similar to medium. We kind of do the same thing. We do a multiply here. We have to get the lower 32 bits. We do 2 times 3, and then we do 6 times this value to get EAX, and then we subtract the X value, which is, I believe, this, and then we get that. We get a counter. We do the same thing with the G colors thing actually, and we get the next color, and then we store that into the code. Then we call XOR WOW again, reperform that rotation. We add 1 to the counter, and then we leave. So we do that once again 4 times because the code is of size 4. At this point, the code is generated, and yeah. So what does that look like in Python? So in the Python, it kind of looks like hell. No, yeah. So we have to do XOR WOW 4 times. So XOR WOW kind of looks like this. This is what XOR WOW looks like. I hate Python, basically. So the reason there's a lot of ands with that is because Python does not like when you truncate. Python does not like to truncate its values because Python doesn't have a limit with 64 bits or 32 bits. So you have to truncate them manually. So I have all those ands there. So you redo all this XOR WOW stuff, and then you eventually get the hard value. Yeah. An index, we get the index, we add that, we do XOR WOW again, and then we just continue over and over and over again. Then eventually, you get the flag once you solve it. So hopefully this doesn't fail again. Yeah, you get the flag, and you're done. That was stupid. Basically, the point of the Ret2 challenge, they just wanted to give you hell. That was an awful reversing challenge as far as I'm concerned. It was not good. I hated this. It took me like 6 hours. This was awful. Because basically, there was no dynamic analysis here. You didn't really need to do any dynamic analysis. That's why I kind of didn't really like it. You could literally just look at the code, every register, and it's essentially instruction for instruction, reconstruct this entire code in Python. That's basically what you had to do. And that was boring as hell. I'm gonna be completely honest with you. That was not good. Yeah. But hey, you got this cool water bottle. So you know, yeah, we're good. Anyway, so that's so does anyone have any questions about it, I guess? That was a lot. If you're more interested in exactly what went into solving it, there's this thread right here that we talked in a lot. I know Brad talked in it a lot. Yeah, and that's kind of where most of the discussion happened. Also, shout out to Daniel. Yo, my guy, he got me this water bottle because I didn't go to Shmoocon. So yeah, shout out to him. Yeah, that's about it. Thank you.